Welcome back, everyone. In this super quick video, we're going to compare linear and binary search in terms of how many comparisons they make, and we're going to look at real timing from Java code. If you don't remember linear or binary search, please go check out the video before where I do a quick review of the two algorithms and their code. Let's start by just understanding what we mean when we say comparisons. We're talking about the number of checks each algorithm will perform while they're trying to find an element. Imagine for a second that we have an array of 1,000,000 or 1,000,000,000 elements. This is million, but I actually increases that. I put even more in there. So imagine that we are using our linear search. Our linear search, if it was looking for an element in 1,000,000,000 items, and it doesn't find it, it would have had to search 1,000,000,000 items to check whether or not it existed. Now, in a binary search, the worst case is actually only about 30 comparisons. It's nowhere near as many as a linear search. And this is why we can really start to see the power of a binary search over a linear search. Now, the difference between about 30 comparisons and 1,000,000,000 comparisons is quite a large gap. This is that exponential reduction that we really need when we're dealing with large data sets. And if we were to graph these two values by number of elements and number of comparisons, we would see what is known as logarithmic growth, something you're going to learn about in the future. I've put together some comparison code here where I'm going to make an array of 1,000,000,000 items. Yes, the size of the array is 1,000,000,000, and we're going to put all the numbers in between effectively 0 and 999,999,999. And that is going to be our target value. We are going to look for that target value that we will find in the very last spot of our array. So what I've gone ahead and done is put together that same timing code that I've used in other videos, where we can actually see the difference in the timing between these two searches. So we're actually going to get a couple different numbers come out of this. The first number we're going to get is the number of comparisons that were made. A comparison is basically the time that we take to go and grab two elements and compare them to each other. Like how many times we have to compare our target element to the element in the array that we're looking at. So in a linear search, if we know we have 1,000,000,000 elements and that we're going to need that very last element, we understand that this number is actually how many comparisons we're going to be doing, right? We're going to actually have to compare, this number, 1,000,000,000 times before we're going to find it, because we're going to have looked at 0, 1, 2, 3, 4, all the way up to 1,000,000,000 before we find our value. For binary search, like I said, without getting into all the math, and you'll have an opportunity to do that math later on, I'm telling you it's going to take about 30 comparisons. Now, comparisons might be somewhat helpful, so I am printing them out, but really what we're here to look at is the time. How long does the time take? So it does take a second just because 1,000,000,000 elements is a large number of elements. Now we can see here the linear search is going to take about 1,000,000,000 comparisons, just as we said, and we can see that it did find the target value where it was looking for it. We can also see that the time it took was about 278 milliseconds. Now we have the binary search that took 30 comparisons. We also found it at the same place, so we know that this worked. And the number of milliseconds it took didn't even register. What if we're looking for something that doesn't exist? Let's go looking for -1. We know that that doesn't exist in our array. Let's go ahead and just show what happens in this scenario as well. So again, we did all of our comparisons. We did not find it, and it took 649 milliseconds. Whereas here we did 29 comparisons. We did not find it, and that again did not even register in terms of milliseconds. And maybe milliseconds when we're dealing with this much data is not that much, but we're just dealing with primitive ints. This isn't really fancy data. It's just a starting place for us. Now imagine we sort of enter the real world where we're dealing with big data that looks like objects, that looks like many different strings, that looks like many different connections. And we can see how this difference in time would actually save us a lot of time as our data set grows in size and in complexity. And that's it. The comparisons and the timing and everything all packaged up. Linear search checks everything, and binary search eliminates everything it doesn't need to check. In the next modules of this topic, we're going to look at some sorting algorithms so that we might be able to understand different ways that we can sort our data and the trade-offs between sorting our data and running our searches. Thanks everyone, and see you there.